Hello and very welcome. My name is Dr. Lucas du Plessis. I'm a senior lecturer in the Department of Mechanical and Aeronautical Engineering, and we are busy with the postgraduate module Dynamics with the acronym msd780. Today's lecture is lecture 9, and it's also the 5th lecture in the section we are busy with, namely application examples that Professor Nick Ravesh explains in detail in his textbook, Planar Multibody Dynamics, the 2nd edition. And Professor Nick Ravesh also included these application examples in his MATLAB algorithm, the dynamic analysis program, which he compiled for the body coordinate formulation. So let's look at the mind map that we've been discussing the other application examples with in the past few lectures. Today we will look at the conveyor belt and friction that is explained in subsection 8.1.4. Now this example, and I'll show a diagram of this, a schematic of this conveyor belt in a short while. I first want to explain friction as discussed in section 4.5 of Prof. Nick Ravesh's textbook. So, friction force may be imposed between two contacting bodies to oppose their relative motion. Friction force can be a function of the material of the contacting bodies, the shape and roughness of the contacting surfaces, relative velocity, normal force, lubrication, and other factors. So therefore, determining the force caused by all possible forms of friction in one formula is not possible. In general, friction is known either as Coulomb or viscous friction, or as a combination of the two. Consider the two bodies being in contact as shown in figure 4.11. Okay, 4.11a shows the two bodies in contact, and 4.11b shows the resultant normal and reaction forces. Now let us assume that each body applies a normal force, F subscript n, on the other, causing a pair of friction forces, superscript F, opposing the relative motion. Okay, and this is what is shown here in figure 4.11b. Coulomb friction, also known as dry friction, may exist even if the two surfaces do not move relative to each other. Viscous friction, we'll get to viscous friction in a bit. If the relative motion between the two bodies is 0, Coulomb friction is computed as static friction, superscript SF, abbreviation for static friction, equals mu s times Fn, where mu s is the coefficient of static friction, and Fn is the normal force that we spoke about and that is shown here in figure 4.11b. So when the relative motion is non-zero, the friction force is determined as dynamic friction, superscript dF, an abbreviation for dynamic friction, equals mu d Fn, where mu d is then the coefficient of dynamic or kinetic friction. Assuming that the dynamic friction is not a function of the relative velocity, and the transition from static to dynamic friction is instantaneous, equations 4.39 and 4.40, the equations we just spoke about, can be presented together graphically as shown in figure 4.12a. So this is our starting point, a very basic explanation of Coulomb friction. Let's look at viscous friction in a bit more detail. Viscous friction, also known as wet or lubricated friction, is proportional to the relative velocity of the contacting surfaces. This type of friction can be described in its simplest form as superscript Vf for viscous friction. F equals mu V times V subscript I, j, where mu V is the coefficient of viscous friction and V subscript ij is the magnitude of the relative velocity Vi minus Vj, or relative speed. If the coefficient of viscous friction is not a constant and is a function of the normal force, then the viscous friction force may be determined as, this is shown here in equation 4.42, the viscous friction force equals kV times Vi, j times Fn, where kV is another description of the coefficient of viscous friction. Okay, so that's viscous friction. We look now at Coulomb friction, a very simplistic explanation, and we also looked at viscous friction. Okay, now when friction is assumed to be a combination of both Coulomb and viscous frictions, the combined models can be presented as shown in figure 4.12b, whereas the relative velocity increases, so does the friction force. Okay, so it has been found experimentally that the transition of friction force from zero to non-zero relative velocity is not instantaneous, but it takes place during a short period of time. Okay, and just to explain that, this is this transition over here, this portion over here, from positive mu s Fn to positive mu d Fn, and also the transition from minus mu s Fn to minus mu d Fn. Okay, and this transition, this instantaneous transition, is also depicted here in figure 4.12b. So this transition, known as the Strebik effect, is depicted in figure 4.12c. And now you can see that the transition is not instantaneous, but happens over a short period of time. Now, implementation of Coulomb and viscous frictions, including the Strebik effect in the equations of motion of a multibody system, is not difficult, as long as the relative velocity of the contacting bodies is not zero. Okay, and obviously this vertical line here, this is where the relative velocities between bodies I and j is zero. Okay, so what we're saying here is, as long as the velocity is not zero, modeling Coulomb and viscous friction, including the Strebik effect, is not difficult. Okay, but how do we handle, that's now the question, how do we handle this momentarily stationary relative velocity? The difficulty arises when the relative velocity becomes zero, the stiction phase, during which the static friction force could be anywhere in the interval from minus mu s Fn less than or equal to the static friction force less than or equal to positive mu s Fn. Okay, so the force can be anywhere along this line. The relative velocity is zero, and there is not a unique value for the friction force with that zero relative velocity. Now, to remedy this problem, the static friction force can be assumed to vary from minus mu s Fn to plus mu s Fn during a short range of varied relative velocities in the vicinity of stiction. And this is shown in figure 4.12d. Okay, so now we don't have a vertical line at zero relative velocity. This line is slightly sloped. Now, a variety of analytical formulas to closely represent the force velocity characteristics of the function of figure 4.12d can be found in literature. One example is the function that we will show momentarily, and this was derived by Anderson and his colleagues in 2007. So the model by Anderson and his colleagues is shown here in equation 4.43, and there are a few things to note though. Before we look at that, the general shape of this function is shown in figure 4.13 that you can see on the screen. So when we look at this formula and model in more detail, the viscous friction VFF, this last term in equation 4.43, can be defined as either equation 4.41 or 4.42, which we spoke about and showed earlier in this lecture. In addition to the coefficients of friction and the relative speed, equation 4.43 contains other parameters, each of which can change the shape of the function. And we'll look at how the function is affected by these parameters next. First, let's look at the coefficient of sliding speed, Vs. This coefficient is present in equation 4.43 below the line of this exponent. It changes the shape of the decay in the Strebik region as shown in figure 4.14a, where a smaller value of this parameter results in a sharper drop from the static to dynamic friction. So here you can see Vs being 0.005, there's a sharper drop from the static to dynamic friction. And if Vs is larger, 0.002, the drop from static to dynamic friction is much more gradual. Now the exponent P, which is present in equation 4.43 in this location over here, affects the drop of the static to dynamic friction in a different form as shown in figure 4.14b. Okay, so here you can see, depending on the value of P, now the bigger P, the greater the value of P, the more rapid the change from static to dynamic friction coefficient. And if P decreases in magnitude, the change from static to dynamic friction regions is more gradual. Now the parameter Kt, which is in this location over here, adjusts the slope of the curve from zero relative speed to the maximum static friction as depicted in figure 4.14c. Typical values for the three parameters are Vs being 0.001 meters per second, P having a value of 2, and Kt having a value of 10,000. This value over here. Okay, now a large value for Kt makes the curve in the static friction region almost vertical. Okay, and we know that we want to avoid a vertical line. So the value of 10,000, there's still a slope in this transition stage or state, so that would suffice. Now we should also note that with this friction model, the maximum value of the static friction force does not reach the desired value of μsFn. Okay, so this curve here in figure 4.13a, this peak and the valley, they come short of the desired value μsFn. One can see that also looking at figures 4.14a, b and c. Depending on the value of the parameters, the peak the peak changes, so it has an effect, and we may therefore consider a larger value for μs to compensate for this shortcoming of the model. Okay, so that was one mathematical model for the implementation of the Coulomb, viscous and Stribic effect. Coulomb friction, viscous friction and Stribic effect. There's also another model. Another example of an analytical formula that closely represents the force velocity characteristics of the function of figure 4.12d that you can see on the screen here is as follows. Okay, and this was developed by Brown and McPhee in 2016. Okay, and is given by equation 4.44 that you can see on the screen. And in this model, VR, which is here below the line, equals the relative velocity between bodies I and J, Vij, divided by Vt. And Vt is the transition velocity, indicating the velocity at which the friction force reaches its maximum value and the transition from the static to dynamic region begins. Now, typical representations of the friction model of equation 4.44 for different values of the parameter Vt are shown in figure 4.15. Alright, so there you get the idea. And here you can see now the advantage then of this model is that we reach the specified μsFn peak regardless of the value of Vt. Okay, and one can decide now based on your model which value you want to use. Okay. Right, the model also suggests that the viscous frictions should be represented as, and this is shown here in equation 4.45, okay, where the parameter Vnt, called the transition force, specifies the required minimum normal force for viscous friction to take place. However, the viscous friction in this formula 4.44, which is shown here at the end, can also be defined as equation 441 or 442 that we spoke about in the beginning of the lecture. Okay, so we had a closer look at two examples of analytical implementation of the friction force versus relative velocity behavior of two bodies. Okay, so to wrap up this section of the lecture, a friction model can also be considered between bodies of different shapes, such as the example shown in figure 4.16. Okay, so two rectangular blocks, if we look at the planar representation, or a sharp object on a flat surface, or a round object on a flat surface. Okay, if the normal force Fn is the result of a contact represented as a penetration model, such models are discussed in section 11.2, and we will talk about section 11.2 in our next lecture, where we have contact between a falling pendulum rod and ground. So the friction force could be categorized as an applied force, However, if the contact is modeled as a constraint for which a Lagrange multiplier represents the resultant or resulting contact force, the corresponding friction could be categorized as a reaction force. Okay, so the friction force, in other words, depending on how you want to model the contact, can either be categorized as an applied force or as a reaction force. Okay, so with that overview of friction force, let us now look at an example, or the example that we are currently, or that we are wanting to discuss, namely the conveyor belt and friction. Okay, so the spring mass system shown in figure 8.14 is a typical example that has been used in literature for testing and comparing different friction formulas. Okay, the block, just to explain figure 8.14, the figure that you can currently see on the screen, the block rests on a conveyor belt that moves at a constant speed. As the block moves with the belt, it stretches the spring until the force of the spring overcomes the friction force and pulls the block back, and the process is then repeated. Now, for this system, let us consider the friction model of equation 443 that we spoke about a few moments ago, as well as the following data. Okay, and there you can see the list of all the input parameters. So the mass of the block is 1 kilogram. The spring stiffness is 10 Newton per meter. The initial length, or the undeformed length of the spring, is 0.8 meter. Gravitational acceleration 9.81 meters per second square. The speed of the conveyor, x dot conveyor, is 0.1 meters per second. Mu s, these are the coefficients associated with the friction model. Mu s being 0.2, mu d being 0.15, mu v being 0, p, the parameter p, equals 2, and kt is 10,000. And then finally, the stiction speed Vs is 0.001 meters per second. Okay, but I will show you in NICRADAP, in the input files, where we have populated these values. So in this model, it is also assumed that the velocity of the block at the initial time is 0. Okay, so when the simulation starts, the block is at rest. Okay, so now we note that the normal reaction force on the block is a constant and is equal to the weight of the block. This Fn here in figure 8.14 is, in other words, exactly equal to the weight of the block. Okay, so let's now look at exercise 8.11. The first task for us to do is to simulate the response of the model for 6 seconds. Now, in order to do that, let's look at this hand-drawn sketch of the block on the conveyor. I've indicated a few dimensions here. I've also added some of the parameters for the spring, as well as the mass of the block. I've also indicated the conveyor and the rotation of these conveyor idlers being clockwise, so that the speed of the conveyor is in the positive x direction. And I've also indicated the global XY coordinate system on the sketch. What I have not indicated, and it is trivial to add that, but the local Cassini eta axes for body 1 will obviously be positioned or located at the center of gravity, and for this setup it would make perfect sense for us to define the local z-axis parallel to the global x-axis, such that the orientation of body 1 will remain fixed at 0 degrees. The angle between the global x-axis and the local z-axis is 0 because these two axes remain parallel. Okay, so with that said, let's quickly look at the input MATLAB files before we run the simulation. That's what you can see here on the left hand side of the screen, and I've opened them in alphabetic order. That's how they are also listed here in the directory models under the subdirectory CB for conveyor belt, acronym for conveyor belt. Okay, so in Animate we've been discussing the inanimate file in all our previous examples. So this inanimate specific, or this specific inanimate input file is not really very complex. There are no points anim to be defined for this simulation. What we do is we define a rectangular shape for the block, okay, and in order to do that we define the W parameter, which equals the length of the block as 0.4 meters and the height as 0.2. Okay, but this is not anything new. We have defined blocks in some of our previous models as well. Okay, then this is also the same or similar to all our previous examples, the parameters for defining the animation or plot axes, and this, as you already know, defines the window size for our animation. Okay, that's in Animate. Let's look at in bodies. Our mechanism only has one moving body, which is this block, and that's body 1. Okay, we already said that the mass is 1 kilogram. Okay, we did not specify this earlier, but the moment of inertia for this body is also defined as 1 kilogram meter squared. Then the initial position for the body, this B1.r, and that's where these dimensions that I've indicated in my hand-drawn sketch come in. So the initial x coordinate for body 1 is 1,0, and the initial y coordinate is 0,2, as you can see here in my hand-drawn sketch. Then you can specify the fact that the initial velocity for body 1 is 0. So 0x component and a 0y component for the initial velocity. If you do not specify these initial velocity components as 0, the DAP program will use zeros as the default. Okay, and what you can also see here in this input file, the initial orientation of body 1 is not specified. Hence, the default value of 0 radians will be used by the program DAP. Then finally, bodies will obviously, for this multi-body mechanism, consist only of B1. There is only a single body in this multi-body mechanism. Right, so that's in bodies. Let's look at in forces. This is now a bit more interesting, and here we have what is referred to as a PTP, a point-to-point force, and this represents the spring that you see here in this diagram. Alright, so I will talk about the other parameters of this point-to-point force in a moment. Let's just look at the textbook, Prof. Nikraves's Multibody Dynamics, Planar Multibody Dynamics textbook. and specifically subsection 4.4.1, applied forces. So point-to-point springs are the most commonly used force elements in mechanical systems. So it's well worth our while to look at how Prof. Nikravesh defines these force elements. Okay, so assume that the force element in figure 4.7 that you can see on the screen, this force element here, in other words, is a spring that is attached between two bodies, body I and body J. The force of this spring is computed as superscript S for spring force, F for force, equals K multiplied by, in brackets, L minus superscript 0L. And this is expression 4.26. Okay, so in this expression or equation, K is the spring stiffness, L is the deformed length of the spring, and L0 is the undeformed length of the spring. Now, the deformed length L is determined from equation 4.23, where we say that L squared equals D transposed multiplied by D. Now, let me just pause there for a while. This vector D that you can see here in figure 4.7, in order to calculate the components of vector D, we just need to look at the vector loop. Okay, so not shown in figure 4.7, but just imagine our origin being here at this corner of figure 4.7. So we will have a vector originating at the origin and ending at point B. This will be our vector RB. And similarly, we can define a vector, once again, emanating from the origin, ending at point A. Okay, so this will be our vector RA. Now, if we take the vector loop, we can clearly see that RB plus D will be equal to the vector RA. Okay, so if we now isolate D on the left hand side of the equation mark in our imaginary equation, we can say that vector D will be equal to vector RA minus vector RB. So very simple. It's just a vector loop, very simple. So hence, if we have the coordinates of points B and A, we can find the components of vector D, and with the components of vector D known, we can find the deformed length of the spring. Okay, so let's carry on. The sign convention for a spring force is defined as positive in tension or pull and negative in compression. Now, this is a sign convention that Prof. Nikravesh proposes, and it obviously works well, so we will stick to that. The forces that the spring applies on the two bodies are given by equation 427. Okay, so the spring force on body I equals the negative of the magnitude of the spring force multiplied by the unit vector u. Okay, now if we just think about this, or just consider this a little bit more in detail, okay, the unit vector u is in the direction indicated here in figure 4.7. Alright, so if we have a pull force, if this actuator, this spring is, or this force element is pulling on body I, it will mean that the force that is acting on body I is in the opposite direction to the unit vector u, and that's why we have this negative sign over here. Okay, now similarly, imagine this force element being a spring is pulling on body J. It will mean that the spring force acting on body J is in the same direction as unit vector U. Okay, because the spring is pulling on body J. Hence, there is the force, the spring force on body J equals the magnitude of the spring force multiplied by the unit vector U. Okay, so equation 427 is valid in both tension and compression. In tension, we just spoke about that. Okay, so this is now referring back to equation 426. Okay, so in tension, the deformed length is greater than the undeformed length, L0. Therefore, this spring force magnitude is positive. So the bodies are pulled toward each other. Right, and in compression, it's just the opposite. There, the deformed length is smaller than the undeformed length. Therefore, the spring force in equation 426 is negative. So the bodies are pushed away from each other. Alright, so I've got a small spring here in my hand, and just to explain or illustrate what that second thought is saying, or second bullet point. So in compression, the deformed length is less than the undeformed length. Okay, and it is, if I do this to the spring, it's pushing my fingers apart, away from each other. Okay, so the same is obviously true for tension, where the deformed length is greater than the undeformed length. And then if you imagine holding a spring in your hands and you pulling on the spring will be pulling your hands toward each other. So let's now quickly look at the other input parameters for this point-to-point force F1 that we are busy defining. Okay, so we specify point IP and point JP. Okay, so that will correspond then, in other words, to point A here in figure 4.7 and point B. Okay, now let us quickly look at what point 2 is and what point 1 is in the input files, in the input file in points. Alright, so point 1 is on body 0, which is ground, and it is at coordinates 0 in the x, 0,2 in the y direction. Okay, so if I can just scroll away here for a little bit. So this is point P1, in other words. It is at the origin on the x-axis and at coordinate 0,2. Okay, then point P2 is on body 1, which is our block, and it is at local coordinates 0, 0. So I already spoke about the imaginary local coordinate system, or the local coordinate system that is not shown. It's not an imaginary, it's an actual or a real coordinate system, but is not shown. So, but be that as it may, the origin of that coordinate system is at the center of gravity of the block, and that's where our point P2 is. Okay, so if we now scroll back to this explanation of a spring force and we look at in forces. Okay, so IP index IP is 0.2, which is on our block, if you remember, and point index JP is on ground. That's point number 1. Okay, straightforward. That's all we need. The other parameters in terms of defining this vector, the vector D, and once we've defined vector D, we have the deformed length. Obviously the undeformed length, that's entered separately, but we want to calculate the deformed length. If we then have the stiffness, which is also entered here as 10 Newton per meter, we can calculate the spring force, and this is a default value that you don't have to specify. This DC stands for damping coefficient, and the reason why that is there is it is possible to have a force element that is a combination of a spring and a damper. Okay, and if that is the case, the damping coefficient need to be specified. Alright, but if you don't specify the damping coefficient, DAP uses the default damping coefficient of 0. Okay, so F2, our force F2 is weight. Okay, and we've spoken about weight also in all of our previous application examples, so nothing new there. And then F3 is a user function, a user force. Okay, and that relates now to our friction force between the block and the conveyor. Okay, so let me quickly then, while we at it, jump to user force and just see how we define this user force. Now, if you remember, it was asked for us that we should use the friction model of equation 4.43 with the following input parameters. Okay, so what you see on the left hand side of the screen is an extract from Prof. Nikravesh's textbook, Planar Multibody Dynamics, equation 443. So here you can clearly see, and this was Anderson et al. Anderson and his colleagues defined this friction model in 2007. Now, the way that Prof. Nikravesh implemented equation 443 in his DAP MATLAB algorithm, you can see here on the left hand side of the screen. Okay, so in user force, this is now equation 443, Anderson et al. So we define all the input parameters that we've listed here on in the mind map. Okay, specifically mu d as being 0.15, mu s as being 0.2, mu v being 0.0, vs being 0.001, p being 2, and kt being 10,000. Okay, we then define the normal force Fy as being 9.81. Okay, the speed of the conveyor is then defined as 0.1 meters per second. The next line of code calculates the speed difference between the block and the conveyor. Okay, and it does so by taking the conveyor speed and subtracting the x component of the velocity of body 1. Okay, and that's done by taking bodies, the 1 dot r underscore d, and we're looking for the x component, which is the 1 that you see on the screen. Okay, just to emphasize the point a little bit further, let's quickly look at Appendix B that Prof. Nikravesh wrote. And here you can see that RD is the time derivative of X, which is the first component, and Y, which is the second component. So that's why we are interested in the X component of the velocity of body 1, okay, which explains this formulation over here. So the next line of code calculates now the friction force, and it does so by calling a function named friction underscore A, and it passes the parameters mu s, mu d, vs, p, kt, v, that we've just calculated, and fy that we've calculated earlier. Now to locate this function friction A, it is under formulation forces friction A, and it's simply a line of code that follows from equation 443. Okay, the viscous friction is not included in this line of code here, and that is why if we go back to user force, Fx is now calculated as the friction force plus mu v multiplied by v multiplied by the normal force Fy. Okay, so that now adds the viscous friction component. Okay, then the next line of code just simply says that the spring force has an x component, which is Fx, that we've just calculated, and there's no y component. And now we take this spring force and we add it to the externally applied forces of body 1. Okay, and that's what this line of code over here does. Alright. Okay, so that's user force. Let's look at infuncs. There are no functions defined for this multi-body system. The conveyor belt in joints, this is also something new. There is a single joint which is a translational joint. Okay, so let's just quickly look at how this translational joint is formulated so that we can understand the input parameters for this translational joint. Okay, so if I can scroll down a little bit, translational joint, and in order to explain translational joint, let's look at subsection 7.2.2. So a translational joint allows two bodies to slide relative to one another along the axis of the joint. To construct a translational joint between bodies I and j, we describe one point and one unit vector along the sliding axis on each body as shown in figure 7.4a. Now these points are pi and pj, and the unit vectors are ui and uj. Okay, and that's indicated here in figure 7.4a. Now the vector d is defined by connecting points pi to pj. Okay, and this is, I've explained this earlier. If you take the vector loop, you get to the formula vector d equals vector rpi minus vector rpj. Now the necessary and sufficient conditions for the two bodies not to have relative translation perpendicular to the sliding axis and not to have relative rotation are obtained by enforcing uj, ui and d to remain parallel. Now let's look at how that is done. Okay, so two vectors that remain parallel implies that their vector product is 0. Okay, so this uj rotated transpose multiplied by d is just a formulation of the vector product between vectors uj and d. Okay, and that must be 0. And similarly, the vector product between vectors uj and ui also need to be 0. Then we have enforced these two conditions that we just mentioned a minute ago. Okay, now just explaining this first part of equation 719, the left superscript t is for translational and 2 is for the number of equations removing 2 relative degrees of freedom. Okay, now if these constraints are enforced, a sliding joint is formed between the two bodies as illustrated in figure 7.4b. Okay, now this ties up again with figure 7.4a. So this is in its exploded view, if you like. This is now in its assembled view. And here you can clearly see the unit vectors don't have to be on the translation axis, as long as the unit vectors remain parallel to the translation axis. But the points, the 2 points, they definitely have to be on the translation axis. Okay, so where we are heading with this is we want to see what the Jacobian submatrices for the two bodies, what those submatrices look like, so that we know what we need to define in the input file such that the DAP dynamic analysis program can populate the system Jacobian matrix. That's where we're heading. So the time derivative of equation 719 provides the velocity constraints as shown here in equation 720. The second line of equation 720 has a simplification. Okay, if you look at the second row of the top line of equation 720 and you compare that to the second row of the second line of equation 720, you can see that there is a simplification. How did we get to that? The second position constraint, okay, if I can refer you to 719, this is the second position constraint, stating that ui and uj must remain parallel, resulted in the constraint phi dot I minus phi dot j equals 0, which implies that there is no relative rotation between the two bodies. Okay, and once you have that simplification, it's very simple to then get to the third line of equation 720, and from that we can then clearly see what the Jacobian submatrices look like. Okay, so the translational joint Jacobian submatrix on body I is shown here on the left of equation 721. So all we need is all we actually need to get the transpose of uj rotated is the unit vector uj, and then for this term over here, all we need is once again the unit vector uj plus the point P on body I. Okay, and that we already have. Okay, and you can follow a similar argument to understand the Jacobian submatrix for the translational joint on body J. The first one was the Jacobian submatrix on body I, and the second one, the Jacobian submatrix on body J. So now looking at the parameters that we've specified for this translational joint, it hopefully will make sense now why we've defined the 2 points, point P on body I, point P on body J, plus the 2 unit vectors, U I and uj. Okay, so with these input parameters from equation 721, it's clear that we can populate the Jacobian matrix of this multibody system. Now, just to complete our discussion here, the time derivative, because that's the other thing for the equations of motion, we also need the right hand side of the acceleration equations, and in order to do that we need to take the time derivative of equation 720, that's shown here in equation 722, and the time derivative of the second row of the Jacobian matrix yields all zeros. The time derivative of the first row becomes what you see here, and from that we can multiply this row by the array of velocities. We take advantage of the fact that the two angular velocities of the bodies I and J are equal, so we can simplify the array gamma, which is the right hand side of the acceleration equations, as shown here in equation 723. Now, you don't need to memorize any of these equations. The reason why I'm showing you this is, once again, looking at the terms. What do we need to populate the right hand side of the acceleration equations in DAP? We need uj, we need ri, the position of body I, position of body J, we need the angular velocity of body I, once again uj, ri dot, the velocity of body I, velocity of body J, the angular velocity of body I. Okay, and similar, so the point is, everything that we need has been specified here in inputs in joints and then also in U vectors. Okay, so just to explain that, our first U vector, U1, is on ground, body 0, and it has local components of 1 in the x-axis, which is the local axis system for ground, and 0 in the y direction. And obviously the magnitude of this unit vector is 1, which is what it is supposed to be. Now similarly, U2 is now on body 1, okay, and its local components are 1 in the local Cassini axis. Remember, we've defined the local Cassini axis of body 1 to be parallel to the x-axis, so that's why it absolutely makes sense that this U vector will have a local component in the Cassini direction of 1 and in the eta direction of 0. Once again, you must ensure that this unit vector has a magnitude of 1, which for this case it is also true. Okay, so once again, just jumping back to in joints, our I index U vector is U vector number 2, just like our I index point P is point 2. This point and this unit vector, both of them are on body 1. Okay, so that's important to have those two correctly numbered. Otherwise, your forces will have the wrong sign. Okay, and similarly, our J point index as well as our JU vector, both of them are on ground. Okay, so it's important, as with the index point and u vector, those two indices must be on the same body. The same for the j indices, they must also be on the same body. Okay, so that's the input file in joins. We've looked at in points, we've looked at in u vectors, we've looked at the user force, and that's it for the input files. So we are now ready to run the simulation. So to run the simulation, we will go to the command window, we will clear our workspace, we will clear our command window, we enter DAP, our folder is contained, or the model is contained in folder conveyor belt CB. Do you want to correct the initial conditions? Yes. So here you can see our corrected coordinates are as we've specified it. X is 1, Y is 0,2, and the angle of body 1 is 0. And the corrected velocities for body 1 is also 0 in the X, 0 in the Y, and 0 angular velocity. Now we need to enter the final time, which is 6 seconds. Our reporting time step I'm going to select as 0,01. Just before I press enter, you will notice that the simulation runs quite a long time, and I will comment on that at the end after the simulation run. Okay, so it's clear it took quite a while to run the simulation, and I just want to point out that the length or the time it takes for the simulation to run is not affected by the reporting time step that we specified. We've specified quite a small reporting time step of 0,01 seconds or 10 milliseconds, but if you run the simulation with a larger reporting time step, for example 0,1 seconds, the simulation takes the same length of time to run. And Prof. Nikravesh explains the reason why in his textbook. He's saying that when we execute DAP, we should notice that the simulation takes much longer time than most other simulations. This is due to the phase when the block is in stiction. That is, it is moving practically with the same speed as the belt. In this phase, the integration algorithm takes very small time steps, and it is the time steps that the integration algorithm takes that determines the length that the simulation is run. Having said that, why would we select then a smaller reporting time step, and when will we select a larger reporting time step? And the reason for that, the reason for smaller reporting time steps is so that we can plot smooth graphs. Your reporting graphs will have straight lines and will have edges if you plot them using a large reporting time step. So for plotting smooth graphs, we will select a fine reporting time step like we've done now, 10 milliseconds, and we can plot our results. When will we then use a large or a coarse reporting time step? That is for animation purposes. If you want your animation to run quickly, remember I said in an earlier lecture that the animation is really a sanity check to see whether the simulation performed as we expected. So there we don't want to wait a very long time and the animation makes small increments. We want it to move quickly. Now, in order to get that right, we will select a coarse reporting time step. So let's now carry on with our exercise. The next task is for us to plot the coordinate of the block in the x direction versus time. Now, the commands that I recommend we use are shown here on the screen on the right hand side. I just want to copy that. Before I run the commands, you must run the abbreviation POST for post-processing, and then we can plot the results. Okay, so the first line says plot all the reporting time steps, that's capital T, comma R, that's the position vector for all bodies for all the reporting time steps. So the colon is all the reporting time steps. The first one is for body 1, because remember we only have a single body, which is the block. Body 1 is the block, and we are looking for the x coordinate of the position vector. And the x coordinate is the first coordinate, so that's the reason for the third one. Okay. And then what I do here in the second line, this MATLAB command axis, that just scales both the x and y axes of my plot. And I'm not too worried about the x axis, because we know we're running the simulation for 6 seconds. So we will start at x or time 0, and we will end at x or time equals 6. But the y-axis is the one that I want specifically to correspond to the results presented by Prof. Nekravesh in his textbook. And there I've used 0,5 as a minimum and 1,5 as a maximum. Okay, so if I enter that, then you can see the plot. I've also copied the plot in my mind map, and this corresponds visually to the solution presented by Prof. Nekravesh in his textbook. The aspect ratio is not the same, and that's why the amplitudes of my graph is a bit larger than the amplitudes of Prof. Nekravesh's graph. But we have good confidence that the simulation ran successfully and that the results are accurate. Okay, so let's look at the second task, or the third task of this exercise. We now want to plot the velocity of the block in the x direction versus time. If I can copy these two lines of code paste it in my command window. So now the first line is to plot all the reporting time steps and the velocity vector of all the reporting time steps of body 1. That's the one that you see here in the position number 2. And we're looking at the x component of the velocities. X being the first component, that will explain the 1 in the third position. Okay, and as for the positions, we also scale our axes to correspond to the results that Prof. Nikrovic published. Okay, so if I enter that, okay, that's the velocity. Now this is an interesting graph because what we see here is, okay, first of all, it does correspond visually, although the aspect ratio is not the same, but visually we can see the response corresponds to what Prof. Nikrovic reported. What is interesting is, so at time t0, the block starts with a negative velocity. So it's moving in the negative x direction towards the left hand side. Okay, and then at around 1 second it is now moving in the positive x direction. So it's starting to move with the conveyor belt until it reaches, or it moves. There's no relative movement between the block and the conveyor belt. They both move at the same velocity of 0.1 meters per second. And this behavior is repeated throughout the 6 seconds time span. Okay, now let me just finish all the results. So the last task is to plot the acceleration of the block in the x direction. So let me just copy these commands. I paste it in the command window. So now it is plot all the reporting time instance, capital T, comma, RDD, which is the acceleration vector for all the reporting time steps. We are looking for body 1, that's the one in the second position here, and we're looking for the x coordinate, or the x acceleration, x component of the acceleration, which is the first component, and that's the one in the third location there. Okay, and as before, we once again scale our axes of the plot. So let me enter that. Okay, and this is once again copied in the mind map, and it corresponds visually to what Prof. Nikrovic reports. Okay, so this behavior, this velocity behavior, can easily be also visualized in the animation. And in order to do that, I want to rerun the simulation with a coarse reporting time step. And once that is done, I will then run the animation. Okay, so I've run the simulation. I now want to run the animation. So I type in the abbreviation anim for animation, and we can press a key to continue. So in that animation, you could clearly see the behavior depicted here for the velocities in the x direction as well as the acceleration, but clearly you could see the velocity behavior, the movement of the block on the conveyor belt. Okay, so with that done, we can move on to exercise 8.12, and here Prof. Nikrovic asks us to repeat exercise 8.11 but this time use the friction model of equation 4.44. So we did speak about this friction model at the beginning of the lecture, but for ease of reference, I want to refer us to the textbook where Prof. Nikrawes explains this friction model in his chapter 4. Now you can see equation 4.44. Now what is interesting to note is that this VR that is referenced here is the ratio of the relative velocity on Vt, where Vt is the transition velocity, indicating the velocity at which the friction force reaches its maximum value and the transition from static to dynamic region begins. Okay, so for Vt is suggesting 0,001 meters per second. Right, the other important thing to note here is that in the implementation, and I'll show that in a minute, the viscous friction is included in the implementation in friction underscore B, which is the function that we will be using. And the way that it is implemented is at the hand of equation 445, which has another ratio of the normal force relative to F subscript NT, where the parameter FNT, called the transition force, specifies the required minimum normal force for viscous friction to take place. To show you how I've implemented this friction underscore B, the call to friction underscore B in my user underscore force M file, I've just added this bottom portion over here. So let's go through it line by line. So as before, as with the Anderson model, the Brown and McPhee model also needs mu S, which is 0,2, mu D, which is 0,15, and mu V, which is 0,0. And then this Vt that we spoke about earlier is 0,001. Okay. Then for the call to friction underscore B, we now need to specify a normal, the transition force. The transition force, which we also just spoke about earlier. And for this example, I just put in the same transition force as the existing normal force. If you remember, the block weighs 1 kilogram. Our gravitational acceleration is 9,81 meters per second square. So that the normal force is 9,81 newtons. And what we're saying here is, if we make what we are investigating is what will happen if we make this transition force exactly equal to the normal force. Okay, then as before, we specify the conveyor speed. We calculate the speed, the relative speed between the block and the conveyor as before. The normal force is 9,81 newtons, and then we call function friction underscore B, and I can quickly show you what that function looks like. It's basically a coding of the equations 444 and 445. So nothing strange there. The last part of my user force input file is exactly the same as it was before, where I say that the spring force has an X component, no Y components, and the external forces acting on body 1 is then appended with this spring force. Okay, so that's how that is done. Now to compare the results with the results of exercise 811, Let's just see how I went about doing that. So I ran the Anderson model. I ran the simulation using the Anderson model. I then plotted the position of body 1 in the X direction. I scaled the axes, and then I entered this command over here, this hold all, and that enabled me to then rerun the simulation with the Brown and McPhee friction model, and plot on top of the existing plot the new positions of body 1 in the X direction. And I made sure that the second plot is now a dashed line. Okay, and this is what the results look like. They are not exactly the same. Okay, so very interesting development. Okay, the same goes for the velocity. So very similar commands entered, and this is what the comparison looks like. So what is clear from the velocity plots is that the velocity of the block, the amplitude actually increases for the subsequent cycles. Okay, it does not remain constant. I think the same is true for the Anderson and his colleagues friction model. It's not constant, but on that graph it's not that visible. But here you can clearly see with the Brown and McPhee model, friction model, the amplitudes actually increase for the subsequent cycles. Okay, and then lastly, the accelerations. Once again, similar commands that I've entered in Octave. And now we notice some discontinuities in the accelerations. Okay, and I'm not investigating that further in this lecture. If you are interested, you're obviously welcome to have a closer look, do a few more simulations, change the parameters, especially this transition force, see what the effect is of that. If you change that value, unfortunately, what we don't have also is we don't have an experimental setup where we could verify the simulation results. But be that as it may, the simulation gives us a very competent tool with which we can now analyze and investigate the frictional behavior between two bodies. And with that, thank you very much for watching. Our next lecture we will be looking at contact between bodies.